You know, we make thousands of decisions every day, little ones. Should I grab a jacket?
Mhm.
Well, that depends, right? Is the temperature below, say, 60 degrees?
Right.
Or do I order the pizza tonight? Well, only if I have more than 20 bucks and I actually finish that report I was putting off.
Our whole lives are just uh, a series of conditions and outcomes.
Exactly. And we as humans, we just get that. We
Yeah.
understand it intuitively. But how does that art of choice translate into the digital world?
Yeah. How does a computer, which is all about following a strict sequential list of steps, suddenly decide to do one thing instead of another?
That question is, I think, the perfect entry point for today's deep dive.
It is. We're getting into the absolute structural basis of how computers think. We're talking about flow control structures, or as most programmers just call them, conditional statements.
It's like learning the rules for digital triage.
That's a great way to put it, because if you look at our source material for today, the core idea is really simple. Conditional statements let you write rules that make a block of code either run.
Or get skipped entirely.
Exactly. And that's the mechanism. That is what lets a computer move beyond just being a calculator and start, thinking and making decisions.
So that's our mission today. We are going to break down the building blocks of this logic from the simplest possible piece of data all the way up to those complex multi-step decisions that run pretty much every app you use.
And you're going to see that every digital gatekeeper, from a password check on your phone to a complicated government eligibility form, is built on just a few of these core ideas.
Okay, let's do it. Let's start at the very, very bottom. For a computer to make any decision at all, it needs a reality check, something simple.
Something binary.
That's where Boolean values come in, right?
That's it. Boolean values are the foundation. They're the simplest data type possible because they only have two states.
True. Or false.
True or false. Nothing else. Every single digital decision. I don't care if it's a program simulating a galaxy or just figuring out your taxes.
It all boils down to a sequence of true or false checks.
And to create those checks, we have to generate what are called Boolean expressions, which is just a fancy way of saying any statement that the computer can look at and say, yep, that's true, or nope, that's false.
Okay, so if true and false are the raw material, how do we shape them? How do we build that expression?
We use tools called comparison operators.
The workhorses.
They really are. Yeah. And it's important to understand they are binary operators, which just means they always need two things to work.
One thing on the left, one on the right.
Yep. And the result of that comparison is always, and I mean always, going to be either true or false.
Let's nail these down. There are 6 of them. We need to be able to check for equality first, right?
Right. And the first one is the double equal sign.
And this is a huge tripping point for beginners. It's asking the question,
Mhm.
are these two things exactly the same?
Exactly.
Yeah.
Because the single equal sign, that means something totally different. That's for assignment.
You're telling the computer, make this variable equal to this value. You're not asking a question.
A very common, very frustrating bug when you're starting out.
Okay, so we have equal 4 is equal to. The opposite is...
The exclamation point followed by an equal sign. That checks for inequality. Are these two things not the same? If they're different, the result is true.
Got it. Then we get into size.
Relative size, yeah. You have for greater than, and of course for less than. Is the value on the left bigger than the value on the right?
And then we round out the set with the ones that are a little more inclusive.
Or equal to versions. So for greater than or equal to, and for less than or equal to.
And with those 6 tools, you can basically create any simple true-false question you need.
You can.
So now we have our true or false result. We've asked the question. How do we turn that answer into an action? How do we make code actually run or not run based on that?
Okay, so this is where we bring in the big keyword, if, as in if condition.
The gatekeeper.
It is. The if keyword looks at the condition you put inside those parentheses. If that condition evaluates to true, the block of code right after it gets to run.
And if it's false?
The computer just skips right over it, bypasses it completely, and moves on to whatever's next.
And we can structure this in a few main ways, these conditional selectors.
Right, there are 3 main patterns. The simplest is the one-way selector.
That's just a lonely if statement all by itself.
It's an optional piece of code. If the condition is true, do the thing. If it's false, just move on. Nothing happens.
But a lot of the time, you need a guaranteed action. You need an alternative.
For sure. Think about a login screen. If the password is correct, let the user in. Otherwise,
You have to show an error message.
you have to do something else. There has to be an alternative path.
And that brings us to the two-way selector.
This is where you use the if statement and you follow it up with an else statement. If the if condition turns out to be false, the program doesn't just skip ahead. It automatically jumps down and runs the code inside the else block.
So one of those two blocks is guaranteed to run. It's one or the other.
Always. Mutually exclusive. But, the real world is rarely that simple. It's not always just A or B.
Right. What if you're assigning a letter grade based on a score? There's A, B, C, D, F.
Or a shipping system that has different prices based on weight. You could have dozens of different paths.
And for that, you need the multi-way selector. I love the analogy in our source material for this. It's like a multiple choice question where there's only one right answer.
It's perfect
Yeah.
because you start with your if, but then you can have one or more elif statements.
Which just stands for else if.
Else if, yeah. And you can chain as many of those as you need.
Yeah.
And then optionally, you can end the whole thing with a final else to be the catch-all.
And the key thing to understand here is the flow, how it actually executes.
Oh, this is so important. It's all about efficiency. The computer starts at the very top with the first if. It checks that condition. If it's false, it moves to the next elif.
And the next, and the next.
Until it finds one that's true. And as soon as it gets a true result, it runs that block of code. And this is the crucial part. It immediately skips the entire rest of the chain.
It jumps right to the end of the whole structure.
It does. It doesn't waste time checking condition 5 if condition 2 was already the right answer. It's a huge performance saver in complex programs.
Let's go to the next level, because this is where things get really powerful. We can take those simple true-false results and combine them. We can build these massive nuanced conditions using what are called logical operators.
Your logic gates and, or, and not.
This lets you ask much more interesting questions.
For sure. It's not just, is your age over 18? It's, is your age over 18 and is your income over $50,000? You can connect multiple conditions.
So let's look at the rules for these, the truth tables. Let's start with and.
Okay, and is the restrictive one. The bouncer at the club. The truth table for and is clear. The final result is true only if condition A is true and condition B is true. Both have to be true.
If either one of them is false.
The whole thing is false. It demands full compliance.
That's my pizza example from before. I need money and the finished report. If I have the money but the report's not done, I don't get the pizza. The whole statement fails.
Exactly. Now contrast that with or. Or is much more permissive.
Or is easygoing.
Yeah. If your rule for ordering food was, I'm hungry or I'm bored, you only need one of those to be true.
And the whole thing becomes true.
Right. The truth table for or shows that the only way for the result to be false is if both A and B are false. If either one is true, or if both are true, the result is true.
And the last one is the simplest. Not.
Simple but powerful. Not is just negation. It takes whatever Boolean value comes after it and flips it. Not true becomes false. Not false becomes true.
It just reverses the polarity.
That's all it does.
Okay, but what happens when you start mixing these? Like, you have 4 different conditions connected with ands and ors. That can get messy really fast.
Oh, absolutely. And that's why understanding the order of evaluations is so critical. It's just like math, where you do multiplication before you do addition.
There's a pecking order.
There is. Generally, not gets evaluated first. Then all the AND operators are evaluated. And finally, the OR operators are handled. If you don't pay attention to that order, the final true or false result of your big, complex expression might not be what you expect at all.
Okay, so let's stack these ideas. How do we build truly deep decision trees? The kind of logic that might, say, power a self-driving car or a medical diagnosis tool.
For that, you use nested conditionals.
So an if statement inside another if statement.
Precisely. Think of it like a multi-stage security checkpoint. The outer if statement might check your passport, only if your passport is valid, if that's true. Does the program even bother to go inside and run the next check?
Like scanning your fingerprint.
Exactly. The inner condition only ever gets checked if the outer one passes first.
And if that outer condition is false, the program just skips that whole nested block.
The whole thing. It's another way to build really efficient layered logic.
We can tie this directly to one of the classic exercises from our source material, the grade conversion problem.
Right. Converting a number score, say 0 to 100, into a letter grade, A through F. This is the perfect use case for that multi-way selector we talked about.
Because you have to check a series of ranges.
You do. And you have to do it in the right order. You always want to start with the highest criteria first.
So you'd say if the grade is greater than or equal to 90, assign an A.
Correct. Then your next statement would be an elif. Elif, the grade is greater than or equal to 80, assign a B. Then elif for 70 for a C, and so on.
Now, hold on. The source material has a really interesting detail here that I want to point out because it's a great teaching moment. It says 80 and above is a B, but it also says 60 and above is a B. That seems like it could cause a problem.
It seems like it, but it highlights why that sequential flow is so important.
Yep.
Let's say a student gets a 95.
Okay.
The program checks the first condition. Is 95 greater than or equal to 90?
Yes.
It assigns the A, and then what does it do?
It stops. It skips the rest of the chain.
It never even gets to the line that checks for 80 or 60. Now, what if the score is 75?
Okay, so it skips the 90 check, skips the 80 check, and then it hits the greater than or equal to 70 line. That's true. It assigns a C, and it stops.
You got it. The structure itself prevents those kinds of contradictions because of its top-down first match wins flow.
Another great practical example from the sources is an eligibility check, like figuring out if someone can vote in a U.S. federal election.
Yes, and that is a perfect example of where the restrictive and operator is essential.
Because you can't just meet one of the criteria.
Not at all. You have to meet all of them. You must be 18 or older, and you must be a U.S. citizen, and you must not be legally disenfranchised. If any single one of those conditions returns false,
The whole thing fails.
the entire expression becomes false, and the program executes the else block, which would say ineligible.
It's just amazing how fundamental this is. When you look at the list of practice problems in the source, these Katie's problems, things like elevators or
Or two
cysts,
stones, yeah.
almost every single one, no matter what it's about, requires you to use conditional statements somewhere to guide the logic. It's unavoidable.
Because any program that does anything interesting has to make choices.
So let's wrap this all together. What have we learned today? We started with Boolean logic.
The true-false foundation of everything.
Then we learned how comparison operators create those true-false values by testing data.
And finally, we saw how the three selector types, one-way, two-way, and multi-way,
Yeah.
use those values to actually control the flow of the program, to tell it which path to take.
When you connect this to the big picture, what does it all mean?
It means understanding conditionals is really understanding how to structure knowledge, how to automate decision-making. It's the difference between a simple calculator that just follows one formula and a program that can, intelligently respond to input and navigate complex real-world rules.
It's the core of computational intelligence.
It really is. And before we go, I want to leave you with a little challenge, one pulled from the source exercises that combines everything we've talked about.
Okay, let's hear it.
Imagine you need to write a function. It takes two inputs, a day of the week, like Wednesday, and a number of days to add, let's say, 19.
And its job is to figure out the new day of the week.
Exactly. Now, to solve that, you're going to need arithmetic to handle the 7-day cycle, but then you'll need conditional structures to map the resulting number back to the correct day name.
So what combination of, say, modulus arithmetic, logical operators, and a multi-way selector would you need to build that accurately?
That's the logic puzzle. That's what we want you to go and think about. Go explore that problem.